16 people is going to speak, 5 minutes each, strict, and the panel will make a small comment of about each of them if they wish, because later all the speakers will have lunch with them, and they will sit distributed. They will not sit next to each other. They will sit with the speakers for all the questions that they want to ask them in both directions. I know the ones who are going to speak here are a little bit nervous. Some of them have told me very intimidated, but I can assure you that no, these Nobel Prize are not what they used to be. They are very nice people. Very nice people and very gentle. In fact, I also had the opportunity when I was a student to speak in front of a Nobel laureate, and after we became great friends, and he has been here, but he asked me a question at the end of my talk, and these guys would be much nicer. The question was, Pedro, where did you learn English? And I said, being very arrogant, a Basque, of course, in Oxford, sir. And he said, did you ask for your money back? I don't think you will have a nastier comment. So please, Fernando.
Thank you, Pedro. First of all, I would like to thank our prominent panel of scientists for being here, and all the participants. And as you know, our panel is formed by Professor Dudley Herschbach, Nobel Prize in Chemistry in 1986, Professor Claude Cohen-Tannoudji, Nobel Prize in Physics in 1997, Professor Jean-Marie Lehn, Nobel Prize in Chemistry in 1987, and Professor Ciechanover, Nobel Prize in Chemistry in 2004. They cover different aspects of physics, chemistry, and biology, and we start with the first participant in order to keep our schedule in time, because as Pedro has mentioned, we have 16 speakers, participants, and we need to be very, very strict with the time schedule, okay? So, our first speaker is Dr. Albert Mateu from Biodonostia Institute.
The research interest of our lab is the molecular mechanisms involved in the regulation of cancer and aging. We mainly focus on the role of stem cells has in these two processes. It's well known that the function or the activity of these stem cells decreases with aging. However, it's not exactly known whether this decline is a cause of the consequence of the aging. We are trying to find with different mouse models whether this is a cause of the consequence. This is more or less a part of the group that is working on aging. Regarding to cancer, in the last year there is significant amount of research and a significant amount of controversy regarding a population of tumor cells that are called cancer stem cells. Some of the researchers really believe on them. I am among them, so this is the research line that we are working. And other people, they think that they don't really exist. So what I think is that there are some tumors where this population has been described. And the relevance of this population is based on their functional activities that they have been indicated that these cells are the origin, the responsible of the origin, the maintenance, and the recurrence of the tumors. So what we want to know is which molecular mechanisms are involved in these processes. There are different mouse models that have been generated that indicate that the cell of origin of this cancer stem cell is alteration in stem cells. So the connection or the link between cancer and aging, it can be in this kind of cell of origin. No? So a research interest of the group is to know the genes that are implicated in adult self-renewal, means the genes that are implicated in the normal regulation of the stem cells, which is their function in cancer and aging. So we are studying their function, as I said, in aging and also in cancer, and associating the role in therapy and in prognosis of the patients. So this is more or less a brief summary of the research that we are doing in our group. Thank you very much.
Can you be more specific?
Regarding, for instance, we are working on the SOX genes. So SOX genes, that are genes that have been described as originally in the development of the different embryos, but now they are already described as well as regulators of adult stem cells. And we have some data, well, we and others have already described that they have relevant functions in tumor origin, tumor progression, and also in metastasis. And regarding aging, it has been shown that the response decreases with aging, but again, a concept that I think it's really interesting is to see whether the increased expression of increased activity of these genes can, in one side, maybe delay aging, or in the other side, induce tumor progression.
There's been recently work in Spain on the expression of the Yamanaka factors in vivo.
This is the, well, it was my previous boss, Manuel Serrano. So it's a little bit, what they have demonstrated is that they activate this Yamanaka factor, these four transcription factors, and what they do is induce tumors in vivo. So that is one of the results that, the consequence of the activation of this transcription factor. And that has the potential input that maybe in the future, with the activation of these factors in vivo, can be used for reprogramming and tissue regeneration. That is a nice network. We are working with some of them. For instance, one of the factors is SOX2, that it's implicated in the Yamanaka factor. So we are.
Thank you, Ander.
Thank you.
Oh, any other? I think that's very easy. Okay.
I just wanted to add one comment, though you were not specific in what you said, that the picture of cancer unfortunately becomes awfully complicated. From the time of 10 years ago that we believed that there is one or two mutations that we should be able to tackle, we are now facing an avalanche of mutations that we still cannot distinguish between hitchhikers and drivers. And the problem of cancer is mostly genomic instability. I mean, what underlies cancer is the fact that the genome is unstable relative to the healthy genome, which also explains to us, but we cannot do much about it, why people become resistant to therapy. We start a therapy, they start to respond, and then they develop another mutation, and another mutation, and circumvent the therapy. So, unfortunately, I suspect that at least for some cancers, the way is quite long.
Yeah, absolutely.
And it's an age-related problem, but one solution may be to compare sequences of DNA of aged people that do have or don't have cancer, and then to compare and at least to try to nail down the most sensitive genes. That's just a comment.
Yeah, that's a good point. Okay, thank you.
The next participant is Dr. David from Ciechanover.
Thank you. So, good morning. I'm David. I've been working in my project for 2 years at MIT, and now I have a third year here at Nanobune under the supervision of Professor Luis Buesson. So the title of my project is High Efficiency Light Emitters with Organic Semiconductors. So what's a light emitter? An organic light emitting diode, or OLED, is an organic semiconductor with 2 electrodes. When applying a voltage between these electrodes, one electrode injects electrons into the organic semiconductor and the other injects holes. So the electron and the holes can recombine, producing light. But this is a very simplified picture of the OLED, because in fact, before the recombination takes place, the electron and the hole forms a quasi-particle called exciton. And this exciton has many interesting properties. many of these properties are determined by the total spin of the exciton. The total spin is a function of the alignment of the spins of the electron and the hole that form the exciton. I don't want to go too technical, but depending on the total spin, the exciton can be a singlet or a triplet. And this is important because only singlets produce light. In a triplet, the recombination is through indirect mechanisms which are non-radiative. Now, how many singlets do we have in a conventional OLED? So a simple calculation shows that if the electrons and holes have random spins, we will have only 25% of singlets, which means the efficiency of the device, the maximum efficiency of the device will be 25%. The efficiency of the device is just the number of photons we can get from the device divided by the number of electrons we are injecting. So is it possible to increase the efficiency? Yeah, it is possible if we increase the number of singlets. So also a simple calculation shows that if we control the spin of the currents, if we have a fully polarized current of electrons and holes, if we have a spin up or down, then we can double the number of singlets. So we can double the efficiency of the device. And this is the purpose, the aim of my project. There are many technological challenges to produce this spin polarized OLED because we need to inject in a very efficient way a spin polarized current into the organic. We need to do the electrodes very close, below 100 nanometers, in order to avoid the depolarization of the current through the organic. And then we must be able to extract the light from the organic semiconductor also in a very efficient way. We think, or my approach is, instead of doing vertical structure, I'm doing lateral structure, which means I must do EV lithography. But the common resists used in EV lithography are not compatible with organic semiconductors. So quite recently, it has been developed a new family of resists called fluorinated resists, which allow us to work in organic semiconductors. They are commercially available for research. They are not optimized at all, and most of my work has been optimized this in order to produce the spin OLED, which I hope to produce here at the Nanowiz. Thank you.
The order of magnitude of the lifetime. The
lifetime, yeah. The lifetime of a singlet can be microsecond, yeah. While a triplet is quite small. It can be even a second. So this is a problem. Yeah, this is a problem because before the exciton combine, they can change from singlet to triplet, and then they can singlet to triplet. So this is a problem. Okay. Thank you very much, David.
The next speaker is Rubén González Moreno from the National Physics Center. Rubén?
Good morning, everybody. Thank you for coming to listen to this big presentation about my professional project. All my colleagues and I is expected today to bring here a new experiment, new science. In my case, I take a parallel path that is the tomological development of new experiment and samples. For defining my the background of my activity, I should say that I carry out my PhD work in the nanophysics lab at the CSM here in San Sebastian. This group works in several topics related to the surface science. And in principle, the studies we made is combine different techniques as are scanning probe microscopies and photoemission spectroscopy to study the properties of new structural materials developed using surface science technologies. Well, the traditional studies in surface science has been made using single crystal. These studies were made using flat geometry. The development of the photoemission spectroscopy in the sense of reducing the probe size to microns and even hundreds of nanometers have left behind the flat geometry, considering that a flat surface, a millimeter size flat surface, is excessively large. The group inside the group of nanophysics lab, another alternative geometry has proposed as is the curved single crystals. This curved single crystal compass many different directions of crystallographic surfaces. Then our proposal is establish a company to fabricate and commercialize this product. This company is running in the first steps as the name is Eurocrystal. And it's possible that this evolution seems to be straightforward from the flat surface, but there is a technological challenge that is the alignment, the crystallographic alignment of these curved single crystals. Then the advantages of these surfaces could be that, as is well known, the steps are active sites in surface chemistry and catalysis. The steps interplay with the thin liner growth, and the rest of the steps works as template for the growth of one-dimensional, third-dimensional structures as are wires, stripes, or nanorods. And more or less is a brief resume of the project we are involved in this area. And that's all. Thank you very much for your attention.
I didn't get it. How do you make these curved single crystals?
We polish.
You make them?
We polish.
Pardon?
Polishing.
Polish.
We take the crystal growth and we choose carefully the direction, and we polish to make parallel steps in one special direction we have chosen. It's not random. This is the technological challenge.
And what single crystals of what?
Metals and oxides. We are beginning with working with this because the people, the community tell us what is the hot topic. For now, we want to try with the single crystal metals, and later start with titanium oxide. We have a lot of interest about it.
Can you control the growth, not to polish, to control the growth, like for instance is done at the Weizmann by Meyer Hart and these people, where you control the growth of a crystal by additions, which favor one direction over another one?
Yes, but our idea is make something more microscopic. It's not it's to be some how to say industrial production. The control. This is nano control. It implies high technology, and more. We have to take into account the factor of the cost of the production.
Our next speaker is Dr. David Ciechanover from the University of the Basque Country.
I think no, it's okay. Well, everyone, good morning to everyone. As you can see, my name is David Ciechanover, and I see myself as a theoretical and computational chemist. And I like to believe that my field of expertise includes the development of new methods for the simulation of electronic excited state, their implementation as computational algorithms, and their application to the study of different photophysical processes. Currently, most of my research is driven by the use of quantum chemical models in the quest of new materials for the efficient conversion of solar energy into electricity. Specifically, I'm very fascinated by those processes which generate multiple exciton hole pairs from just one single solar photon. In molecular materials, such as molecular crystals, aggregates, polymers, or even covalent dimers, this is typically called singlet fission. And in singlet fission, we have a photon that hits our system, and then it gets promoted to a higher optical singlet state, which can very rapidly relax into a new singlet state that then can split into two spin triplet states, and eventually these two triplets can decouple and separate, and then we have two pairs of electron and hole that can produce, electric current. So overall, we have one photon in, two electrons out. So theoretically, we could imagine that this process or this kind of systems could double the efficiency of our photovoltaic devices. But of course, there are plenty of difficulties, and it's very hard to experimentally obtain systems with these properties. And computationally, it's also very challenging to simulate the singlet fission. So in singlet fission, we have at the very least 4 electrons which are strongly correlated, and we have to compute, obviously, the ground state and several excited states which have different spin multiplicities and rather different electronic structure properties. But right now, we already have some initial models that can, we believe, can compute or characterize and understand the singlet fission mechanism, and can even be used to predict the efficiency of singlet fission in new compounds. And in the future, I'm real convinced that the joint efforts of experimental studies and computational investigations is the recipe for the success of this alternative path for the use of solar energy. And thank you very much for your kind attention.
Any question or comment?
Are you able to predict the efficiency you hope to get?
I think I'm able to present to the experimental people some possible mechanisms to understand why or why not they do have or they don't have singlet fission in their compounds, and I'm not able to obtain an absolute value, but I can compare different type of compounds and materials. I do believe I can do that.
That sounds like very good information to offer. Thanks.
Thank you. Can you explain to a layperson, complete layperson like me, what is the real technological hurdle of converting the sun energy into electricity? Don't tell me low efficiency. Tell me what is the real technological, what is needed to be in the lab, to do in the lab in order to circumvent the difficulty of making a reasonable amount of energy out of the sun energy. What prevents scientists from doing it?
Well, in single junction materials, we have a theoretical limit, which is the 33rd, like a 1/3 of the energy that we can capture, in theory, can be converted. So that's the theoretical limit.
Still a lot.
Still a lot, but there are two ways. We have to, at the same time, increase the efficiency and decrease the cost. Because right now the efficiencies are not bad, but the cost it's not very good. So we have materials which are very, very cheap, but the efficiency is not that good. And we have materials which are quite efficient, but the cost is quite a lot. So then they cannot be competitive against fossil combustible. So that's one thing. At the more fundamental level, I believe a big problem is the charge separation. So you want to separate an electron and a hole. You don't want recombination, and you have several processes competing here, and you need some design in order to improve this separation, and then to inject this either electron or hole, or maybe both, to your system to obtain electric current.
You have this single splitting. The energy, the outcome is at most what a photon brings in. You cannot get more. You get only 1/3. Okay. So how do you cover the solar spectrum?
Right. So this would
you don't want just one wavelength.
That's a very good. That would cover the higher energy spectrum, right? This kind of this type. Sorry.
The UV, the violet, and the higher energy
and high visible range. So it's just to take advantage of this part of the region and then use other technologies for the lower. Yeah.
Thank you. Next speaker is Dr. Javier Lehn from the Instituto Biodonostia.
I'm working in the Biodonostia Institute, and I am a Miguel Servet Fellow. I started a research line on retinitis pigmentosa a couple of years ago. So retinitis pigmentosa is the most common form of inherited retinal dystrophies. It is consists of a progressive involved a progressive cell a progressive death of photoreceptors is involved, which leads to loss of vision in the patients, and there are like more than 1 million people affected in the world. So I have two main lines of interest. The first one is trying to identify the genetic cause of our patients, most of them from the Gipuzkoa region. And on the other hand, I'm analyzing mouse models of retinitis pigmentosa in the lab, which will be more the topic I'm going to talk today. So we are talking here about an extremely complex genetic disease with more than 80 genes involved, and there is no current treatment available. So the good news is that there are some clinical trials currently going on for a small group of blind people, which are gaining a little bit of vision. But the bad news is that most of the genes are not suited for gene therapy, and also that we have to take into account that gene therapy also only works when in the initial stages of the disease, where the photoreceptors are there. So I'm interested in developing a therapy, a novel therapeutic approach based on the modulation of microRNAs using animal models of the disease. So microRNAs are small RNAs which can bind and modulate hundreds of genes, each of one. So my aim is to use an approach that could expand the viability of the photoreceptors, thus to expand the therapeutic window where a patient could be treated. So the question is, does it make any sense if we consider that most of our patients have the disease caused by mutations in a single gene? Well, I believe it does, and based on the following observations. First, there are some family members in some cases with the very same mutation that they develop a very different pattern of the disease. So this suggests that there should be other factors involved. And also, we still don't know the genetic cause of about 40% of the retinitis pigmentosa. So this suggests that there should be other regions that are non-coding regions in the genome that should be involved. And also, one microRNA can target hundreds of genes, as I said. So our approach would be it would have a broad spectrum of action instead of, like, for instance, gene therapy that is focused only in one gene for each case. So why my interest in microRNAs? So there are several lines of evidence. For instance, it's been described at least two different models of retinitis pigmentosa mouse that they have alterations in mirrors. And we have also a completely different model, and we have observed specifically one mirror which is altered like 40 times increased comparing with the wild type mice. And interestingly, these three models, even though they have mutations in very different genes of this visual signaling, they have a very similar pattern of alteration in the microRNAs. And also another thing is that there are currently tools available to modulate microRNA, and in fact the first clinical trials are about to happen with patients suffering from heart diseases, where an approach using microRNA modulation has been working in mice and is very promising. So therefore, these results, hopefully, they will help us understand a little bit more of this very complex disease on one hand, and on the other hand, will open new avenues for novel therapeutic approaches. Thank you very much.
Any question or comment?
If you have a broad spectrum RNA, will you not hit other targets also?
Yeah. Sorry, the question is, sorry?
You will also hit other targets.
Yeah.
If you have a broad spectrum. So what you gain on one side, you may lose on the other one.
Yeah, so, of course. So yeah, this is one of the caveats of this project. So for instance, the targets of microRNAs is one of the things that is not so easy. So, but there are some approaches like reported using luciferase, which are giving some confidence in your results, and we will use those, for instance.
Thank you. So thank you very much indeed. Our next speaker is Dr. Maria Rebollo from Ciechanover. Okay. So would you need the pointer?
Good morning. My name is Maria Rebollo, and I work in self-assembly group here in Nanogune. I would like to start saying that we can order the matter in many ways. For example, 3-dimensional crystals or 2-dimensional sheets. A big challenge on a nanoscale is one-dimensionality, and the ultimate challenge is an infinite line of single molecules or atoms. Exactly, this is our goal. We are looking to have an infinite line of single proteins. I'm going to present 3 different examples of what it happens in nature, artificially in the lab, and what I am doing with taking something of the nature or something of the lab. In nature, the actin protein can form fibers or filaments by natural assembly. These filaments or fibers have a diameter of 8 nanometers. So this is a nice example for a highly defined, infinite and self-assembly molecular wall. Another example is what we can do artificially with an STM. We can align atoms with an STM tips, and this is the ultimate thickness that we can get. It's an infinite line of atoms, putting them one by one in a line with an STM tip. So let me have a look to to a faster and simpler methods. The forced assembly electrospinning method is a fascinating technique to fiber fabrication. This electrospinning technique is very old, as you can see in the arrow, because it was described in 1897, and in 20s, polymer fibers were fabricated in a micrometer scales. In 80s, the polymers were electrospun in a nanoscale. And over the years, more than 200 polymers were successfully electrospun and characterized depending on their applications. And now, here we are, in our lab, we are able to fabricate single-line proteins. And how we do this? With a protein solution, by applying an electrical field, we get a pure protein fibers. On the bottom left, this is the world record on a electrospun fiber with a nylon fiber. With a nylon molecule of 0.4 nanometers, they can form a nylon fiber of 1.6 nanometers. So currently, we are in our lab. We are able to fabricate a electrospun of albumin fiber of 5 nanometers of diameter. So we are close to this world record, but with proteins, with pure natural proteins. So please let us show you.
Just 1 minute for a demo.
Let's show you a demo of the electrospinning method with a simplified handheld tool with a polymer solution. We can show you our demo.
Hello. So the demo, we have a handheld machine like this. And very simple, we need a solution like this. And then we load the solution into the spider machine.
And we will have a droplet that by applying an electrical field form a jet that where the solvent is evaporated and the jet is elongating, forming a fibers. Maybe here you can see like as the solution is spraying, but it's not spraying. This is a very quickly moving single wire of polymer.
Yeah.
And this is the electrospinning technique with our demo system. Thank you for your attention.
Spider-Man.
Why do you want to electrospin proteins?
We want to check if the functionality is fine or to apply in some applications. For example,
What is the mechanical resistance?
depending on the protein of the viscoelastic properties or the viscosity of the solution that we get with the parameters to get the fiber, the good parameters for doing that.
Thank you.
I'm a researcher at the Department of Theoretical Physics of the University of Helsinki. And I work in cosmology, so I thought maybe the best way was to make a brief sketch of the history of the universe, even though it's too small, so I'm afraid that maybe people even on the front row cannot see it. So essentially everything started with a bang, Big Bang. After that, we had
Speak up a little.
Sorry.
Yeah,
okay.
speak up, yeah.
So we had first of all a Big Bang, and after that we had an epoch of inflation, which essentially means that we were in a period in which there was a huge acceleration, during which we had some quantum fluctuation, which afterwards we raised to the seed of the structure we see nowadays. And we had after that an epoch of radiation, and at the present time we are on an accelerating universe. which means that essentially we are like at the beginning, but where expansion rate is much lower. Now, what caused this acceleration? So that's one of the things that interests me on my research. So for that, what we need, essentially in GR, what we know is that geometry somehow dictates, interacts with matter and the other way around. So if we know the matter content, we can now predict what is essentially the geometry of our universe. So the matter content is what is shown here. And unfortunately, we know only this part. So that's what corresponds to standard matter. The rest is dark, as its name indicates. And that is essentially due to the fact that we don't have really theoretical model that predicts. So dark matter on one side, and then these other chunk, which predicts the acceleration of the universe, which is dark energy. And here I summarize more or less the question that interests me on my research. So first of all, what is causing this acceleration? From an observational point of view or from a logical point of view, we know that we should have something like a cosmological constant. On the other side, from a theoretical point of view, we have a big problem there, because then we have about 120 order of magnitude of this much between what's predicted theory and what we observe. And that's the reason why people have been looking for other models. One possibility is, instead of having something which is constant, something that evolves, which can be quintessence or something that is called quantum energy. So what is the difference between these two? So if we have quintessence, essentially, is something that's make the universe to expand, but in such a way that it decays. On the other side, if it's phantom, so it's, instead of being constant, it grows. Another possible approach is that gravity is not exactly what we expect it is at those scales. So instead of having GR at those scales, we have something else. And in that sense, one can look for modification of gravity, and that's one of the things that I'm interested in. And there are essentially two ways of modifying it, either by invoking that we live on something which is not only four-dimensional, but it's larger, so there are more dimensions, or simply that the Lagrangians that describe the gravity is not Hilbert, but something else, which means essentially we are modifying the curvature itself. Okay? There are more exotic ways, so for example the multiverse, so which are stating essentially that there are as many universes as we can imagine, and one of them is the one in which we live, and therefore it's not so puzzling that we live in a universe which is expanding. But then there is a price to pay, and then we need to use an entropic principle to say why we are where we are. Now, from what we know nowadays, let's say the acceleration of the universe, so the acceleration is almost constant, but it can decay, or it can go faster. So if it goes faster, that might predict some singularities on the future. So we would not have only a big Bang singularity in the past, but we could have some kind of singularity on the future. So what kind of singularity do we have in the future? So this is what is usually referred to it as the big singularity or other kind of singularity. How these singularities are characterized? So they are characterized by the way in which the expansion stops. So say in other words, what happens to the Hubble parameter, which describe how our universe is expanding, or its successive derivative with respect to the cosmic time. And that for people that are interested in quantum cosmology, like in my case, is quite interesting because this gives some new models in which we can see what happened to at quantum scale. And most important, so the quantum scale maybe it's not only at the very beginning, but it can also be something that could happen in the future if this singularity takes place. Okay, and that's it. So thank you very much.
What are the best tests of the computational law at very large distance?
At very large distance, so it's on cosmological scales. So this one can have, this can be coming from supernova, which go out to redshift essentially 1, which means essentially when the universe is half its present size, and so on and so on. But yeah.
Thank you. No more questions? Okay. Thank you very much. Our next speaker is Dr. Dudley from the Center of Materials Physics.
Good morning, everybody. My name is Dmitry, and I'm glad to present today my research work. strong enhancement of circular dichroism in a hybrid material consisting of J aggregates and silver nanoparticles. So it is commonly known that plasmonic nanostructure can enhance, for example, Raman scattering in more than 1 million times, which allow you to detect even the single molecules. But today I want to focus on the enhancement of circular dichroism by plasmonic nanostructures. Actually, what is circular dichroism? Circular dichroism is a difference between left and right circularly polarized line at a given wavelength. And why it's so interesting for us? Due to the fact that most organic molecules in nature, and especially biological molecules, are naturally chiral, and the circular dichroism allows you to measure this chirality of your system and asymmetry of your system. And it's a really nice example when you can measure the conformation of the protein, like alpha helix structure, beta sheet, or random coil. So it means that enhancement of sensitivity of circular dichroism would be really useful for application in, for example, in chemistry or biology, pharmacology, and so on. So that's why currently increase the number of papers which discuss the possibility of enhancement of circular dichroism by the plasmonic nanostructure. And theoretically, it's possible to do. So theoretically, they explain like two mechanisms. From the one side, we have the enhancement of the electromagnetic enhancement of the optical electric field inside of these chiral molecules due to the presence of nanoparticles. From the other side, these molecules, chiral molecules, which are close to these nanoparticles, can induce the dissipative chiral inside of this nanoparticle induced by the electrical dipole of these organic molecules. So in this case, you will see, you don't have slide, maybe you're right. Okay. So you will see in the spectrum of some CD signal. CD signal usually like this, like a butterfly. Not on the maximum absorption of plasmonic structure. It can be silver or gold or whatever. And you can see the CD signal on the absorption of your molecules, for example, biological molecules. So it's really nice because these two processes allow you to see the enhancement not only on the biological molecules and because they absorb in UV range, but on the absorption of the plasmonic nanostructure. And actually in our work we show that it's possible to do. We use G aggregates and the silver nanoparticles, and we saw enhancement in both cases. We saw enhancement in the plasmonic nanostructure, and where we see the enhancement of circular dichroism and enhancement also in the absorption of the G aggregates. So we received enhancement approximately 10 times of circular dichroism by this combining this hybrid structure. So it means that we believe that our research will allow better understand the process of enhancement of circular dichroism by this plasmonic nanostructure, and may have potential application in sensing of like biosensing or whatever. So thank you for your attention. I don't have slides, I just presented.
Sorry for that. Any question, comment, or? Okay. Oh.
Can you not enhance it by doing magnetic circular dichroism?
No, we didn't see actually. I checked it. In this case, for example, for our hybrid structure, I didn't see any enhancement like magnetic. But actually, it was interesting that even the plasmonic nanostructures are sensible to the magnetism. For example, the silver or gold, they can enhance the signal of the magnetic CD. Just so, but in the combined these two structures, magnetism didn't do anything. So we have the same enhancement like
organic molecules.
Yeah. But we wanted to see it, you know, because the plasmonic structure like silver or gold, they're sensible to the magnetic field due to the electronic cloud inside of these particles. But in this case, unfortunately we didn't see like any influence of magnetic field by the organic molecules. We have the enhancement on the plasma maximum of the CD, but we didn't see any enhancement here when we switched to the magnetic field.
Okay, thank you very much.
Thank you.
Our next speaker is Dr. Marek Kresla. from Biomagune, sorry.
Hello everyone. So, no thanks. So, basically, our aim is to produce a protocell. Protocell is a chemical structure that exhibits some lifelike features, but is made in the lab out of non-living matter. So the features we're speaking about is information, the capability of a replication of this information, very simple metabolism, or for example, if it's possible, evolution of this system. So we have to start not with DNA, but our code or our information basically started is the crystal. So this is pretty old idea. Crystal, for example, in this case, we want to use gold particles. So imagine 20 nanometer particles that you can encode the information in the size and the shape, which is basically later translated to the optical fingerprint. So each shape and the size can be basically encoded into the plasma layer. So what we have to do is basically replicate it. Okay, so this system must run a kind of metabolism and go to the, let's say, run via autocatalytic reactions to produce other particles. So in this case, this particle can also absorb the light. So these particles can make very nice chemistry for us. For example, it's possible to reduce molecules like in the NAD to NADH. So this is organic, basically biomolecule that we all have in our body. So you can reduce the simple molecule, and then this strong reducing agent in this state can, for us, let's say, reduce other particles if you have metal salts. So you see, the particles can produce the particles, okay? Just using the light. You will ask where the electron comes from. So for this purpose, we're gonna use water. So this is a very tough reaction because we're gonna split the water to produce the crystals. At this stage, we are able to, let's say, regenerate NAD to NADH. This step is well known. And the tough and the, let's say, challenging part is still this reaction. So if you're gonna go to the protocell, we have to make the body, okay? So in this case, we have to make all these reaction steps inside of the vesicles. And for this purpose, we are using polymeric vesicles, basically copolymers. So we have kind of surfactant, but it is, let's say, polymeric version. We have hydrophobic and hydrophilic parts. They make the vesicles, right? So this vesicle is very stable in the specific solvent composition. For example, DMF and water. Now, if you change the ratio between these two, this vesicle will split into. For example, if you increase the amount of DMF, so hydrophobic part, you will increase the nature of the environment in the sense that this system would like to increase the surface. And we already observed this in the presence of the polymeric mices, that if you increase these components, they would just go in two, and the material inside is basically split equally into different ones. In our case, we have to do an opposite way. So we have to get rid of water, then we change the environments, so that at the end of the day, we basically produce crystal. The system will replicate. During the night, we have to add more water and also the membrane composition, which is the copolymer, and the next day it's ready to run reaction. So you see, this part basically is this kind of photosynthesis, right? So you basically you can produce, you can store light energy in the chemical bond using water as a fuel. So we are doing this just basically to, for new technologies, for example, more sustainable technologies that can not only make the chemistry for us, that can also exhibit several life-like features. Thank you very much.
You can make NADH. Can you make also ATP?
It will be scientific.
You cannot make ATP.
This is just the most simple model we want to develop. Like in this case, we have 5 chemicals. Maybe we will need something like 6 chemicals, and at ATP for chemists, this is pure science fiction. This is very, very complicated.
The problem is the oxidation of water. We will not get it in this way. Very difficult. We have worked on that for many years. It's very difficult to get oxidation of water. The other thing, of course, I like this idea, which in fact people have used NADH to make nanoparticles of gold, for instance, by reducing cooled salts. So making NADH is good. I'm not sure. I think you should use something which is not water, and more easy thing at the beginning. No, at the end it is no good. Try ethanolamine or something like that, where you oxidize the nitrogen, and then it has this is sacrificial reagent.
Yes, in this case we will produce the gold immediately by sacrificial agent.
Sorry, what?
In this case, our sacrificial agent is able to reduce the metal by itself. No light is necessary. So
ethanolamine does not reduce. No, it will not do it by itself. You need to have, I'm sure we worked on this kind of thing. The other thing is also quite interesting, the fact that you do physical splits. You know, probably the work of Lisi at DTH, where they have also physical split in a sort of a metabolism, because they have an inside ester, which they cleave, which makes the membrane components, and then it opens and then they split.
There exist different stories like this, because this is what I said, that during the night we have to add the membrane components. If it will be the autopoietic entity, it should be able to produce the membrane component by itself, like the cell is doing, right? But we are still far from that. Maybe one day.
Long way to go, but that's interesting. Long way to go.
Thank you. Thank you very much.
Good afternoon, and it's a great honor for me to be here today. And I would like to talk with you about the role of the lipid matrix in the nano-ordering of cellular membranes. So the cellular membrane can be defined as a two-dimensional structure, two-dimensional liquid crystal, which is formed by 2 layers of lipids with proteins embedded in this image. So the rate of lateral diffusion in this system should be very quick. It's very fast, and still the membrane somehow controls its ordering at the nanoscales. So of course the cells take advantage of the interactions between its molecular components, and also Swiss attraction and repulsion forces. But which is the role for the lipid matrix? Which is the role for the soft lipid matrix in all this ordering? Why would the nature choose a soft matter to make all this as this matrix? Well, in our lab, what we think is that the intrinsic elasticity and flexibility of the lipid membranes is an active ingredient in the ordering of cellular life. Well, each protein that comes to interact with the lipid leaflet brings in a geometrical deformation to the leaflet. So the deformation energy, which depend on the differences between the geometry of the protein and the geometry of the lipid membrane. And if this deformation energy is bigger than the thermal energy of the system, the molecules then will want to segregate and somehow, basically, simply speaking, curved molecules are going to want to go to curved places on the membrane. So this way we can basically say that the small, highly curved membrane compartments, such as 100 nanometers, for example, transport vesicles, can be formed. And how do we measure the extent of this geometrical wish of a protein for a certain curvature? Well, our in vitro approach in our lab is basically to try to decrease the size of the lipid membrane to be such that it approaches the size of the protein to interact with it. And this way we can measure directly the symmetrical contribution of the protein to the membrane. How do we do that? We start with the flat membrane, and we apply force to this membrane and pull the nanotube. This nanotube is a cylinder, so in order to characterize its shape, we only need to know its length, which is basically set by us, and its radius. And the radius, we can extrapolate it from the measurement of the conductivity of the interior of the tube. For depending on the electrolyte conditions we are working with, we can get to sub-nanoscale precision in the measurement of this radius, and we can measure it within tens of milliseconds. So basically, just to mention here that the smaller nanotubes that we have been working so far were 80 nanometers in length and just 10 nanometers in internal diameter. And this size approaches very well the dimensions of small protein complexes in the cell. And yes, we have tried adding proteins, real proteins, to the system, and the last outcome was published recently in the Science magazine. I don't have time to go into details of this work, but just to mention that we could observe how a small complex of only 20 molecules could constrict our nanotube from being 10 nanometers to being only 6 nanometers. 10 nanometers to be only 6 nanometers in diameter. And we are also trying to tune now the sensibility of the system to be able to resolve the contribution of each one of these 20 molecules to the geometry of the nanotube. And we also are working with other proteins which have different functions to be able to finally say which is the role for the soft membrane in the ordering of nanostructures. Thank you very much for your attention.
Our next participant is Dr. Ainara Vallejo from the Biological Institute.
Good afternoon. So I'm working at Diagnostic Institute as a young researcher in the neuromuscular area. I have been working during my scientific career as an undergraduate student in cardiovascular and neuromuscular diseases, first in the University of the Basque Country and then as a postdoc in the University of California, San Francisco. So my currently interest is on the molecular basis of muscular dystrophies. Yes, and also hopefully to find an effective treatment, finding some targets for these diseases. So what is muscular dystrophy? Muscular dystrophy is a rare genetic disorder with a world prevalence of 1 in 3,000. It causes a progressive weakening of the muscle and muscle waste. It is a devastating and costly disease, and it has no cure currently. So there are more than 30 forms of muscular dystrophy, and they are determined by by different genes and proteins affected. So although in some cases the primary genetic defect is known, in most of the cases the precise pathological mechanism is not. So I'm focusing in Duchenne and muscular dystrophy and calpainopathy or limb-girdle muscular dystrophy because these forms of muscular dystrophy are very common in the Basque Country region. The cause of these diseases are mutations in calpain-3 for calpainopathy and in the dystrophin genes for Duchenne muscular dystrophy. And our goal is to elucidate the pathophysiological mechanism underlying these diseases, and also hopefully to find novel targets to treat these diseases. So the models, to this end I'm using different models, both in vivo and in vitro. First, we are using cells. We are using also muscle tissues from biopsies, from human biopsies. And we are also using mouse models. So the big problem we have encountered in the lab is that none of these models are really perfect to study this disease. And why? First, there is a very serious limitation of muscles because biopsies are not necessary nowadays for diagnostic purposes. Also, cells are currently using human cell lines and also mouse cell lines. Well, first of all, I'm going to talk about mouse models. Mice is a standard animal model for studying genetic diseases, but in the case of muscular dystrophy, it's not that great because mice are somewhat resistant to muscular damage. It looks like this muscle has a high capacity for regeneration. And lastly, muscle tissues, well, cells, yes, sorry. The cells are always an issue with the cells because, you know, culture artifacts, culture viability. Also, there is issues between primary cell lines and cell lines, okay, or primary cultures. So it is not perfect. So we believe in the lab that we need to work at the same time with all the models in order to advance in our understanding of the disease. Fortunately, we have been able to get some relevant tissue samples from the Donostia hospital regarding limb-girdle muscular dystrophy or calpainopathy and Duchenne, and we are working with those. So I would like to talk a little bit about the exciting results we're getting in the lab regarding calpainopathy, or calpain 3 deficiency, calpain 3 here. So we have found that a calcium handling protein, which is CERCA, that is very essential for muscle relaxation and calcium homeostasis regulation, is reduced in calpain 3 deficient samples, both in cells, in human and mouse, silenced cells, and also in muscle tissues from muscular dystrophic patients. So we believe that CERCA could be a great target to test novel, therapeutic strategies. Thank you very much.
You said mice are resistant. Why? Because it's often the case that some animals which have a special relations to some diseases. For instance, mole rats don't get cancer. These are these rats which are on the ground,
sure.
which are
yeah.
And they don't get cancer.
Well,
so people are studying that. Now, in your case,
there are models of muscular dystrophy in mice, but the mice are the dystrophy is very mild.
Yeah. So why?
We believe. I don't think it's tested. It's demonstrated. But they believe it's because the higher regeneration capacity of the muscle. The satellite cells, the pool of satellite cells are always regenerating, so they always lose damage.
So you don't want to cure the disease, you want to have the regeneration faster.
Sure, it would be great to have a higher regeneration, yeah. I think in humans related to mice, we have an third regeneration capacity. That's the way we are.
So next speaker is Dr. John Herrera, comes from the University of Pierre.
First of all, I would like to thank you, the organizers, for giving me the opportunity to discuss about my research project with Professor Ciechanover, Professor Herschbach, Professor Lehn, and Professor Cohen-Tannoudji. I am a material scientist, and as a material scientist, I am devoted to understand the properties of materials from their fundamental ingredients, the electrons and ions that interact and form all the materials we have. So we believe that understanding these properties from the fundamental ingredients will be able, in the future, to create new materials with improved functionalities. So nowadays, our civilization faces tremendous challenges related to especially energy, and we believe that creating new materials with improved functionalities is going to be a key factor if we want to succeed. However, if we want to probe systematically new materials in the lab, this requires a huge effort. If we look at the periodic table, we can see, right now we see that we have an infinite ways of combining different elements and create new materials. So, probing systematically each of these new materials in the lab requires huge human and economical effort. However, right now we have a tremendous computational power, and this provides us with a fabulous workaround in the search of new materials. In the picture you can see Sequoia. This is one of the biggest computers in the world with 1.6 CPUs. So these kind of huge machines that we have now give us the possibility to probe the properties of materials in the computer with calculations before synthesizing them. So we can save lots of effort, and we can do now big science using these kind of machines. I think that politicians are starting to understand that, and for example, the US government created the Materials Genome Initiative some few years ago, and invested $100 million for a systematic search of materials using these kind of machines. I think they characterized 2 million molecules for solar cell applications, if I'm correct. I think we're going to see more and more projects of this type in the future, and many of them might concentrate on the search of ferroelectrics, thermoelectrics, and superconductors, because they are very interesting for applications. Ferroelectrics are very interesting because they can be applied in electronics, and they might be potentially interesting in solar cells. Ferroelectrics because we can create an electric current out of a thermal gradient, but we still don't have very efficient thermoelectrics and superconductors. I think I didn't explain why they are interesting, but we still are missing superconductors working at room temperature. In all these three materials, ferroelectrics, thermoelectrics, and superconductors, vibrational properties are crucial. In ferroelectrics, because they determine if at a given temperature a given ferroelectric is a ferroelectric or not. In thermoelectric, because vibrational properties determine the efficiency of a given material in the energy conversion. And in superconductors, because in many of them, vibrations couple with the electrons to create the superconducting state. If we want to calculate vibrational properties using these machines, we normally use the so-called harmonic approximation. The harmonic approximation is very simple. It assumes that if we displace one atom from its equilibrium position, the force that it feels is linear with respect to the displacement. And we have now very powerful software to perform the calculations of the vibrational properties in the harmonic approximation. However, in many ferroelectrics, many thermoelectrics, and many superconductors as well, this harmonic approximation breaks down, completely breaks down. So if we want to perform a systematic search of new ferroelectrics, thermoelectrics, and superconductors, we are somehow handicapped because we don't know whether we are going to be able to calculate properly their vibrational properties. So my project is very simple. The idea is, develop new theoretical approaches to calculate the vibrational properties of materials whenever the harmonic approximation breaks down. And then, with this code, implement these new theoretical approaches in software that can be efficiently applied in these kind of huge machines that we have now available and we didn't have a few years ago. We believe that with these tools, and if we understand the vibrational properties in ferroelectrics, thermoelectrics, and superconductors, we will open a window for the search of new materials of this kind in the future. Thank you for your attention.
Can you compare the calculated vibration frequencies to experimental observation?
That's the thing. For example, we are working in I'm especially working in solids and in superconductors, and there are cases, for example, where when you calculate the harmonic frequencies, so the phonon spectra in solid, you see that the experimental result does that there are, huge errors. And in some cases, for example, we have done some calculations in palladium hydride, and you see that we can get a good phonon spectra with the tools we are creating. This is because the harmonic approximation completely breaks down in this case. And so we think that the tools we are developing, we will be able to describe vibrational properties in this wide range of materials where it breaks down. And the reason why it breaks down is simple, because it's just because, okay, we have a potential that is something like this, and this is the potential, and this is the displacement. The harmonic approximation tells us the potential, the second derivative at this point, at equilibrium. But this is not enough to describe the full potential. So we are working on tools that will be able to describe situations if we have this kind of case.
We'd like to go the other way around. High TC superconductors, Müller and Bernard, still none of those high-brainy physicists has explained how they work.
Yeah.
And if he hadn't had the material, he would never have found it by calculations.
Yeah, that is true. That is true.
So there's another approach which can be applied using chemistry. This is combinatorial chemistry by using high throughput robotics.
Exactly.
With doing it's brute force. It's not very intellectual, but it may lead to results, which then you have to try to explain.
Yeah, definitely. Yeah, with high TC superconductors, it's true we still don't have the theory to explain, to calculate the superconducting transition temperature.
But nobody knows how it works.
No, nobody knows how it works. It's true. But maybe there are also electron-phonon superconductors where the vibrational properties, the harmonic approximation collapses. And I think if we understand the vibrational properties in these superconductors, maybe we'll have a kind of clue with respect to high TC superconductors, especially because there is some phase diagrams of some of these electron phonon superconductors that are similar to these high TC couplings. But we'll see. But I guess that...
I don't want to sound negative, but I think other properties are probably easier than superconductors.
Sure. Maybe. Yeah, maybe.
The diamond, in fact, is going to shine back with a green light if it contains these ambient centers. Much more than this, if you properly sequence our laser pulses, we can even prepare or change the state of the spin of the NV centers. However, there are problems with some diamonds. The diamond has an appealing appearance because it has very high reflectivity. However, this makes the light detection very difficult, because if we want to detect the light higher with a greater angle than the critical angle, in fact, we will not detect anything due to internal reflections. Another thing is, the diffraction limit of the optical system is determined with about the half of the wavelength of the light. In our case now, that means that we cannot have much more than 300 nanometer resolution. So we want to improve this. We will improve the detection limit by utilizing near-field microscopy. In this method, a sharp metallic tip is in fact just placed over the surface, and on this metallic tip, coherent electron oscillation might appear, which in fact are called surface plasmons. Our light coming out from the NV centers can interact with these surface plasmon, and in fact it can give us back the energy with what we have just given to the plasmons as also light, however with a different angle, making the light detections much more easier for us. So now we can construct these tips with nanofabrication, and in this method we break the diffraction limit of the optical microscopy, because the resolution is determined with the sharpness of the tip. That can be again nanofabricated. There is another additional benefit of using diamond, that we can construct future magnetometers, because the spin levels of the NV centers can be split due to Zeeman splitting when the magnetic field is applied. Therefore, in fact, in a reverse way, we can measure our applied magnetic field, so we can construct a magnetometer that has a sensitivity high enough to even detect a nuclear spin. So our ultimate goal is to correlate changes in the diamond and with NV centers with the magnetic nanoparticles deposited on the sample. So we would like to deposit magnetic nanoparticles and correlate the changes, how they affect the spin levels of the diamond. Thanks very much for your kind attention.
Thank you, Claude. We have one small question or comment.
How many spins can you detect with this technique?
I mean, the point is that we want to, in fact, reverse thinking, so we want to detect as less as possible, because how it's currently done, so you create with, for instance, electron irradiation, a lot of defects in the diamond, and with optical microscopy you have about 300 nanometer or even worse resolution, and in fact you are going to get information for much more than a single spin. And what we want to do is we create many spins on the surface, we place our tip above this NV center and talk to only to the single spin. This is, so we want to communicate into one. But of course, if you just break the resolution, then you can talk to as much as you want, but that's not so beneficial.
What is this? What is this spin? You break a carbon-carbon bond, or what do you do?
No, the spin is in fact coming out that you put a nitrogen in the place of the carbon, and there is a vacancy, and there will be an S1 spin state.
So it's not diamond, it's diamond with some nitrogen.
Yeah, exactly. Sorry.
Okay, thank you very much. Our program. And the next speaker is Dr. from the University
you. Well, thank you for the opportunity of talk about my work here. I obtained my chemistry degree in 2004 in Universidad de Castilla-La Mancha, in which I also obtained my PhD in a work focused on the reactivity of triacyl moieties. In doing this experimental work, I realized how important the theoretical background is important in a successful organic chemistry. And for that, I did a postdoc stage at the Free University of Amsterdam and here in the Euskampus Universitatea, focused mainly in theoretical chemistry and DFT methods. After that, I started applying these acquired skills on the rational designs of organic catalysts. Why choosing proline? Proline is, from all the available catalysts, we selected proline due to its unique structural features. I think it's a natural amino acid which has a 5-member ring in its structure, which is formed by 4 carbon atoms, 1 nitrogen. And it also possesses 1 carboxylic acid in the alpha position of the nitrogen atom. It's known that proline is a really versatile and tunable scaffold in which we can modify the conformational arrangement of the ring by changing the relative position of the substituent of it. With this idea in mind, I try to modify proline's structure in order to improve its catalytic activity or even to obtain products which are inaccessible with the former amino acid. In that sense, our research starts studying in detail the experimental outcome of one selected reaction, trying to figure out all the possible mechanistic pathways. Most of the time, it implies trying to understand the observed results and propose a model. At that point, computational tools are really helpful for checking which of the proposed mechanisms are feasible or not. Moreover, analyzing the structures of the stationary points, we can, of the most probable reaction mechanism, we can find the effect of the catalyst, and therefore we can modify it in the way, and therefore we can modify it to improve it or change its activity. That's our plan. For example, changing the accessibility of one reagent strongly affects the final outcome of one selected reaction. Once the model is proposed, it's mandatory to consider the chemical availability of all the starting materials required to synthesize the catalyst, because it's not only a theoretical work. We need to remember that not all the possible chemical modifications can be done experimentally. Fortunately, there are available synthetic tools that allow the access of a wide family of proline analogs. When the new catalyst is prepared, the next step consists in check if it works. If the proposed model is right and the experimental outcome is the expected one or not. In the best scenario, we can further modify the catalyst and try to obtain selectively all the possible products of that reaction. That means if we have one reaction, we mix 2 reagents and we obtain a mixture of products, only by selecting the catalyst, we can selectively obtain one of the products, and if we change the catalyst, we obtain selectively one of the products. That methodology could be a powerful tool for the preparation of valuable compounds, such metabolite key intermediates in drug synthesis. To conclude, my research plan is focused on the development of chemical models for organic reaction that not only provide a better understanding of the reaction mechanism, but also allows to design an a la carte set of catalysts. Thank you for your attention.
Please turn off the mobile cell telephone, please, in order not to interrupt the speakers, which are very concentrated on their presentations. So we have time for several questions or statements. Okay.
Oh, this is a field I have followed quite a bit. Everybody has worked on proline base. There must be other catalysts which are as good or better. In your type of work where you try to predict catalysis, why do you think proline is so good? And what other structures would you suggest?
At the beginning we selected proline because we can really tune it And we know
there's been hundreds of papers.
Yeah.
Brilliant.
And we also employ beta-lactams and any other scaffolds for design the catalyst. And the main point is knowing proline is well known. We know the structure and we know how to modify it. And in most of the time, we make hybrids between proline catalyst, proline-based catalyst, and another moiety-based catalyst. And the best point of proline is we can control. We know how to control it very carefully. We know it in detail, and that's why we use it.
The conformation is not so sure. It's a 5-membered ring, so it may change. Why not use a 6-membered ring?
I think
morpholine derivative or piperidine derivative with a carboxyl in alpha position.
Because we synthesize proline employing 3+2 cycloaddition, which is really easy to control, and that's not easy for others. For example, 6-member rings. The Diels-Alder reaction is not too easy to control, and with proline we know how to do it exactly the catalyst we want, and that's why we have the idea in mind.
Thank you. So, thank you very much. The speaker is Dr. from the University of the Basque Country.
Okay, thank you very much for having me selected. I'm going to introduce you to my project entitled Epigenetic Mechanisms of Transgenerational Inheritance of Analgesic Tolerance Inducing by Morphine. One of the challenging in biomedicine is to understand how our lifestyle can influence in our health and in the health of the future generation. The idea that human's phenotype is only regulated by gene information is changing dramatically because there are mechanisms that provide a regulatory information to genome without affecting the primary nucleotide sequences. These mechanisms could be considered epigenetics. The epigenetic marks are often relatively stable in a differentiated and adult tissues in the body, where they help to confer a stable cell identity on tissue. The epigenetic marks, such as DNA methylation and histone modification, are established during an organism's lifetime and are irrelevant at the beginning with respect to the next generation. It is believed that oocyte, stem cells, embryonic stem cells, and embryonic germ cells have the capacity to erase the pre-existing epigenetic information and to bring the epigenomic back into a pluripotent state in a process called reprogramming. Natural reprogramming occurs in primordial germ cells, the precursor of mature gametes, and in zygotes just after fertilization. During reprogramming, both epigenetic marks, DNA methylation and histone modification, are completely eliminated. In spite of that, defects in reprogramming occurs, and these may produce the transgenerational epigenetic inheritance. However, the mechanism that protects those elements remains to be determined. In any case, only the epigenetic changes that occur in mature gametes have the potential to contribute to the phenotype of the next generation. On the other hand, one of the most exciting findings about the epigenetic change is the probability that gene expression can be influenced by environments. Stress, diet, toxin behavior, and other factors can regulate the expression of genes. For this reason, the environmental epigenetics is becoming an area of great interest for those working in medicine. Morphine is the most active component of opium and was the first opioid to be isolated. The therapeutic value of morphine for pain relief is well established despite a considerable number of side effects. Chronic opioid administrations lead to a progressive decline in analgesic efficacy. Interestingly, some recent studies describe that morphine has a transgenerational effect on analgesic tolerance and behavior on offspring. Offspring from adolescent morphine-exposed mother produce sex-specific alteration in both emotionality and morphine sensitivity. However, the mechanism underlying the transmission of analgesic tolerance remains unknown. For this reason, the aim of my project is to understand how morphine can induce epigenetic change and which of these epigenetic marks can be important for the transgenerational inheritance of analgesic tolerance in order to predict the potential effects of opioid chronic use in the health of the offspring. In order to accomplish our goal, we are going to develop an in vitro system that allows us to analyze the mitotic and meiotic heritable epigenetic changes inducing by morphine in both primordial germ cells and in early embryo. For this reason, this project not only established an important foundation on basis research on fertility, stem cells, cancer, and aging, but also it could be a great interest to pharmaceutical company because we are going to establish a genetic strategy by which heritability of epigenetic change induced by environmental agents can be monitored in culture cells. Thank you very much for attention.
Can you be a little bit more specific? I understand that you are talking about DNA methylation in this case.
Yes.
Can you point to the genes that are methylated and their expression is shut down and then they are transgenerationally transmitted to the offspring? What type of genes are shut down by the opiates treatment?
At the beginning, we don't know the genes, but we are going to make a microRNA, a micro-expression to identify the target of potential genes. But we thought that the possibility, the most important genes, could be the imprinting genes, because morphine have a sex-specific alteration, so imprinting genes maybe contribute to this kind of epigenetic transgenerational inheritance.
More questions? Okay, if not, thank you very much again. Our last but not least speaker today is Lehn from the Center for Integrative Biology, University of Twente.
Okay.
Do you need a microphone? Or?
I think that I'm low. My voice is low. Okay, to explain my project, I'm going to use a coin that maybe the Nobel Laureates, they know more than me because it's a Nobel Prize. Why I'm using a coin? Because usually the people, when they think about HIV, they only see one side of the coin. That is the reason why the HIV can infect our cells and provoke the unknown disease called AIDS. This disease is caused because the HIV go into the cells, into the immune system cells, and they kill, then reducing the chance of the immune response to fight against different external agents. One of the challenges for the scientific community is to find new or novel drugs that can reduce the level of resistances that appear when we target, and this one is something that usually happens, the standard therapy against HIV target viral components, which means because the HIV has a really high mutation ratio, the virus can mutate itself and create a resistance to these different drugs. One of the challenges for my project is to find new targets that are not viral protein. But what about the other side of the coin? Because what if I say that we can save life using the HIV? The HIV. There are some genetic disorders that we can solve using gene therapy. Gene therapy means that when there is a genetic disorder, mutation in our genes, there is one protein that is not functional or is really working not in a good level. Using the HIV or another viral systems, we can deliver the correct the correct genes into the cells that has this mutation and provoke the in place of this mutation, making that these cells, these infected cells, they can produce the gene that was missing or really in a low levels. But anyway, in both cases, the thing that make the HIV really a good killer and also useful for gene therapy is the integration. What means the integration? Okay. The integration means that when we have a cell and we have the nucleus where the DNA is located. The HIV or the HIV have to cross this barrier, that is the plasma membrane barrier, but after that need to reach the nuclei. To insert the DNA, its genome here, and this one is going to make able that when this cell divide, the daughter cells will get also the DNA that is inserting here. But the HIV cannot float and reach the nuclei with the diffusion. Have to interact with different proteins that are cell proteins. This is why my project is going to find what are the host viral interaction to try to block this interaction. In this case, to block or to inhibit the infection, but also to know how this delivery of the DNA can be helpful for develop of gene therapy. Thank you very much.